Welcome back to CS520. Today I'm going to talk about basic computer architecture, and I'm going to keep it very basic, very simple. But the simple model that I'm going to present will be sufficient for most of what we're going to do this semester. How simple? Just two boxes connected by one double arrow. A CPU connected to memory by a bus. That's it. The main thing we're leaving out here is some way to do input and output. We probably won't talk much about I/O this semester because you will explore that topic in ECE562. Let's dig in a little deeper now to the two boxes in our simplified model. First, let's start with the CPU. As you probably know, CPU is an acronym for Central Processing Unit. It contains three basic components. The control unit, which decides what is done when. It runs the whole show. The arithmetic logic unit, or ALU, which does things like adding two integer values or multiplying two floating point values. And registers. These are locations in the CPU for storing intermediate values. So a program can fetch values from memory into registers, operate on the registers for a while, and then eventually store some results back to memory. One big fact is that memory is much slower than the CPU, so to get high performance it is best to keep operands in registers as much as possible, minimizing the number of memory accesses that are performed. Now let's look at memory. The memory stores both the instructions, the individual operations of a program, and the data that the program operates on. There are big implications of this that we will discuss a little later. The memory is organized as an array of cells, just like an array in your favorite programming language. The index of a cell is known as the address of the cell. So there are two concepts that we need to keep straight: the address of a cell and the contents of the cell. Let's take a look at a simple diagram. Again, memory is just an array of cells. The index of a cell is its address. The contents of the cell is what's stored in the cell. So in this diagram, the memory cell with address 7 has contents 1066. You'll be amazed at how many times you'll get confused about this during the semester and during your career, actually. And we will all do it. It seems hard to believe, though, doesn't it? The contents of memory is just bits. Each cell has a fixed bit length. In modern machines, the size of a cell is always 8 bits. But older machines had much bigger cell sizes. The machine I first learned to program had 60-bit cells. Later in the course, we will explore why there has been a transition over time from bigger cells to smaller cells. But maybe the more important fact is there is nothing else in memory than bits. In particular, there is nothing to tell you what kind of value is in a cell. Is it a character, an integer, an instruction? There's no way to tell. Instead, the program must provide an interpretation for the bits. Let's take a look at an example instruction for a hypothetical machine. An instruction might add the contents of memory cell 1011.7 to register 6, interpreting the two operands as integer values. Note the instruction must specify the interpretation. It must say that we're not just adding, but that it must be more specific, that we're adding two integers. The machine does not remember what kind of things was last stored in a memory location, and the bits themselves do not provide any clues. As we'll see later, when we look at data representation, any sequence of bits can possibly mean a variety of things. But this allows us to do tricky things, like store an integer into memory and then interpret it later as an instruction. This is both tricky and powerful, as we will see. Note that since instructions are stored in memory, they must also be encoded in a series of bits. We will study this later when we talk about program representation. How does the control unit work? Basically, the machine is stuck in this infinite loop known as the fetch-execute cycle. It fetches an instruction, executes it, and then goes to the next instruction. Fetch, execute, on and on, forever. Let's break down the fetch phase. First, it figures out what instruction to execute. Then, it fetches it from memory. Remember, the instruction is just a bunch of bits. So next, the control unit has to decode the bits and figure out what the instruction is, what operation needs to be done. Then it might need to fetch input operands from memory. Now, going on to the execute phase. It actually executes the instruction. And then it may need to store the result back to memory. Finally, it goes back to step one and starts all over. The machine is our slave, stuck in this loop until someone turns off the machine. How does the control unit know which instruction should be executed next? There's a dedicated register which contains the address of the instruction that is to be executed next. This register is known generically as the program counter, or PC. Normally, the PC is incremented during each instruction so that a program proceeds serially through a sequence of instructions. But to implement control flow, conditional statements, and loops, an instruction can modify the PC directly to set it to a particular address. Note that PC is a generic name. Machines could have particular names for this register. For example, the Intel IA32 architecture calls it the EIP register for Extended Instruction Pointer. Since modern machines store both the program and the data in memory, they are known as stored program computers. This design is known as a von Neumann machine after the mathematician who was one of the early modern computer architects. However, note that many people think this gives von Neumann too much credit. But whoever first thought it up, it is a powerful idea. It enables compilers, which are programs that translate programs written in a high-level language, like C++, into the equivalent series of low-level instructions that a computer understands directly. It's nice that we don't have to do this by hand, and we can have a computer do the dirty work. By the way, I also teach a course in compilers. I will probably mention this a few hundred times during the semester. Linkers are programs that combine two programs together. For instance, you write a C program and then you link it with the C library in order to get the code for a library routine that you have called. The linker will combine the compiled form of your program with the code for the library routine that someone else wrote earlier. We can also write self-modifying programs. Since the program is in memory while it is running, it can operate on itself on the fly. This is a mind expander, but it is commonly done on modern systems. For instance, there are dynamic linkers which wait until you call the library routine at runtime, and then they find the code for the routine and bring it into memory so you can then execute it. The dynamic linker is a magic piece of code added to your program behind your back that will modify your program while it is running. Another example is just-in-time translation of Java. Java implementations normally interpret Java bytecode. We will look at this in more detail later, but it is slow to interpret the bytecode. To improve efficiency, the Java implementation can translate heavily used portions of your program to the native instructions for the computer you're running on. This can have a huge impact on performance, and it is a program modifying itself on the fly while it is running. However, the von Neumann design has also been criticized. All data and instructions must pass through the bus, and the bus can be a bottleneck. As we saw, the fetch-execute cycle first must fetch the instructions from memory, then the data from memory, then it executes the instruction, and then it stores the result back to memory. That's a lot of traffic across the bus. And also remember that the memory is much slower than the CPU. So the CPU might, at times, be stalled, waiting to get instructions or data from the memory. We will come back to this throughout the semester. Okay, that is the basics of computer architecture. In future sessions, we will look at data representation. What does a piece of data look like when it is in memory? In particular, what do the bits look like? And we will look at program representation. What does a program look like in memory? And again, what do the bits look like? But let's stop here for now.